important and engaging work. As we get underway, I would like to acknowledge that our institution stands on the unceded traditional territory of the Coast Salish people, particularly the Duwamish. We thank them for our continued use of the natural resources of their ancestral homeland. And thank you all for tuning in. Town Hall is proud to be a community-focused organization and a place where we can share and sustain ideas and creativity, even if it means we can't gather in person. I'd like to thank our speakers for appearing tonight to help make that possible. Tonight's broadcast is also streaming to our Facebook and YouTube pages. For viewers who want to watch this broadcast with closed captioning, we recommend viewing via our YouTube page. The video will be available for rewatching immediately following tonight's broadcast. Even though we've been able to pivot to online programming like this, Town Hall and the nonprofit community at large have been put under significant strain due to COVID-19. We hope you will consider extending your generosity to help support us during this difficult time by making a donation or becoming a member. Town Hall's work is made possible through your support and the support of our sponsors. Our Arno Matulski Science Series is supported by Microsoft, KUOW, Wyncote Foundation Northwest, and the taxpayers of Washington. Finally, Town Hall is also a member-supported organization, so I'd like to thank all of our members watching tonight. Tonight's program will include 3 separate presentations with a time for questions at the end. Each presentation is about 20 minutes long. You can submit questions at any time using the Ask a Question field at the bottom of your screen. If you can be sure to address the question to the presenter you intend it for, that would be greatly appreciated. We cannot guarantee we'll get to every question, but we'll try to get to as many as possible. And now I would like to introduce our first speaker. AJ Balatico is a PhD student in learning sciences and human development at the University of Washington's College of Education, with interests in computational neuroscience and educational equity, especially for science, technology, and engineering and math education. He focuses on how people learn, motivation, and identities from their experiences. Please join me in welcoming AJ Balatico.
Thank you, Candace. Before starting graduate school, I was a high school science teacher and robotics mentor, and robotics is a good hands-on, minds-on activity. But what robots look like, what they can do, and who can build them is constantly being reimagined by some of our youngest learners. I'm always surprised at how these participants in First LEGO League design and build a robot out of Legos for each year's theme and challenge. If we want more young people to become future engineers, scientists, business leaders, educators, and policymakers, then we need to invest not only our money, but our time and creativity to create engaging activities that represent reality. On the left, these students are making a presentation to judges about a community-based project that somehow involves robots. They had to design and build a robot for the robot challenge, and then they had to go out into the community and apply that robot to something that they've seen in their community. On the right, we see a youngling watch a robot pick up trash, and both participation and observation are essential to how we learn. Hopefully, these experiences can help these young students become motivated to pursue more complicated and more meaningful learning throughout their academics. This is the first piece of data that I saw when starting graduate school, and it's hanging in a conference room in Miller Hall at the University of Washington. For a lot of us, our time in school is very important, but as you can see from this graph, most of our time is spent in that sea of blue of informal learning. We all might have different opinions on whether our schooling was positive, mixed, or a negative experience, but for most of our lives, that orange section in the middle, we only spend such a small amount of our waking hours inside of an actual school building, inside of a formal learning environment. We might also consider all of the meaningful experiences that we've had, and what becomes most important to us is highly personalized and contextualized. I think that given our limited time and how precious we know youth is in terms of learning, that we need to find better ways of reaching learners of all kinds. And we know when people can personalize and contextualize their learning, they're happier and more productive. Socializing and building positive relationships is extremely important for healthy development. And we know that positive emotions and feelings of safety motivate people to want to explore and learn more. When we can adjust the environments we're a part of, we can all become better learners. However, in some contexts, stress can be a powerful motivator. So in those circumstances, we want to be able to do what we trained for very well. For work environments, especially in the civil service sectors, we spend a lot of our resources on training and preparation so that we can do the best that we can when we need to. However, once again, these joys and stresses can spill over into other contexts, that formal learning environment. From these pictures, who is at the center of these learning environments? On the right, we have a teacher-centered learning environment, the traditional teacher at the front lecturing. And on the left, we have kids exploring. And neither is inherently more beneficial than the other. And we know that students do best when we mix things up. And that's based on a lot of neuroscience that we will explore in this presentation. We should all have the goal of making people become experts at things that they enjoy doing. So the first part is becoming an expert, and then the other part is finding tasks that we enjoy doing. Informal learning environments can be designed for customizable experiences, and that informal learning can be much more productive and more personalized. A trip to the zoo can be a more memorable way to learn about animals compared to reading something out of a textbook or watching something on YouTube. Learning is a change in thoughts, feelings, beliefs, and behaviors due to our myriad of experiences, and then learning occurs through our experiences. Humans learn because we all have brains and bodies, so this diagram is just a schematic to help us kind of conceptualize the timescales that we're dealing with. We know that we are learning across our entire lifespan, but every second we are getting tons of inputs from all of our sensory organs in our bodies, and that leads to us building upon all of our working knowledge and memories. So our sensory memory is how we immediately react to the environment and how we might react with people. So in building, such as in Legos, we can identify different things that are salient about those particular Lego bricks, some things that are meaningful. So aspects of what we can see, such as the color, the size of the brick, what they can be, what they can eventually become. And then our working memory, once we make a decision about what we want to do, we can set ourselves to a task and organize how we set out to accomplish that task. So in the case of building with Legos, we might want to build a house, and building the house might make us happy, and we might be doing it with people that we enjoy the company of. Over time, we will eventually become more adept at our building. We can design more intricate, complicated structures, and we can eventually compile all of our creations together. This transfer of working memory to long-term memory deals with different structures of our brain and what we are selectively directing our attention to, and we constantly have to retrieve what we're setting out to do. Eventually, when we put all that together, we can, if we keep making Lego houses, we can eventually make a really robust Lego city. So all of that takes a lot of time and a lot of dedication and a lot of effort, and a lot of people, quite frankly, will probably give up a little bit before they get to that Lego city. But those experiences back then, when we're building upon our relationships and just playing with toys and exploring the world, can be highly meaningful to a lot of people. So in order to explore or go into this foray into neuroscience, I wanted to talk to everyone about these three networks that we know that the brain consists of, and how our brain is constantly toggling between these systems. So in shorter timescales, pretty much every minute of our waking lives, we're constantly shifting between this default mode network, going through the salience network, and then over to the executive control network. The default mode network is when we're daydreaming or thinking about ourselves, or even thinking about mental time travel, which is basically a fancy way of thinking about the past, the present, and the future. We can all imagine how we were when we were little kids. We can imagine ourselves how we are now, and we can imagine hypothetical and future selves um, when we grow older. The salience network is the toggle in your brain that shifts between this default mode network and the executive control network, which is the thing that keeps you on task. So if you have to give a presentation or do a homework assignment or cook something for your family, then the executive control network takes over and constantly is in a struggle with the salience network um, for your attention. And the different brain slices, they might look a little bit different, but I've included a graphic in the bottom right corner of what level each of the slices are taken. The brain is very complicated, and there are a lot of structures that if you sliced one way or the other, you wouldn't get all of them. So these pictures are composites of those different brain slices. We know that there are huge differences between, or there are differences between children and adults in terms of their reward and recognition sections of their brain and their decision-making sections of their brain. And both sections are connected to the RFIC. The name, the technical anatomical name isn't important, but the red section you could see is both important for the reward recognition and decision-making section of your brain. In children and adults, for the reward recognition system, in the child, it's a lot bigger and it's a little bit more spread out, while in the adult, it's a little bit more concentrated and more forward in the front of the brain. For the decision-making section, we see the same pattern where we have the more expansive network in the child, while in the adult there's a higher connectivity and a smaller footprint. And that's a very common theme when we look at the differences between experts and novices. And that is one way that we indicate whether somebody has learned something, is whether they are good or more experienced at the task. So in the context of experts and novices, we have lots of different kinds of brain experiments that deal with how different parts of the brain are connected and respond to different tasks. So hockey players, for instance, they watched videos of other people playing hockey and had to guess which way the puck went, so left or right. And then they did the similar thing with badminton, something that they're not as familiar with, whether the shuttlecock went left or right. And we know that the differences between expert and novice hockey players are that expert hockey players, they did better when predicting in hockey, but they didn't do as well in badminton. They were just as bad. However, in both sports, both the the expert brain lit up in a specific pattern that was considered a little bit more efficient. It had a smaller footprint, but the connections were a lot faster and a lot more strong. The context is very important. In some experiences transfer, and in others, we're all novices. However, in things like chess and jazz improvisation, we know that experts are very good and can go into an autopilot or a flow state where they are very good without even thinking about it. Chess grandmasters have played so many games that they know what is a good move without thinking about it. So they're mostly in that default mode network rather than the executive control network, while a more novice chess player will have to think about their moves. A pro jazz musician, likewise, will know what sounds okay or sounds good, and they can play it well and in combination with other things that sound good to create very specific and pleasing musical patterns. We also know that video games are very helpful in neuroscience because they are tasks that you can do while getting brain scanned. So if you were a novice Pokemon player, somebody who's never played Pokemon on a Game Boy versus a Pokemon master who has played Pokemon since you were 5 to 8 years old, and then later when scientists go ahead and take a image of your brain, they we can see very clear differences with respect to looking at Pokemon. So in at the left, we see that the novice player, that brain region doesn't quite light up, but for the Pokemon master, it is very well lit. And then in neuroscience, we have to know why we know stuff. So these controls, the middle and right panels, help us understand that playing Pokemon doesn't increase your vision or doesn't structurally change um, massive parts of your brain. It's only dedicated to those areas. So this kind of suggests that we expose people to different tasks, and some of them will stick from early childhood and can potentially be more productive than just becoming a Pokemon master. But um, presumably the theories would go that if we have genuine learning experiences, then they would transfer over into adulthood. And then before GPS and ride shares, we know that taxi drivers, we have done lots of brain scans on them, and we know that they have demonstrably different brains compared to other drivers. And a lot of us do drive, but taxi drivers, because they do it um, as their primary profession, um, their skill level is a little bit higher and they can make better judgments than most amateur drivers or people who drive just or non-professionally. So cool, we know uh, we can do all these fun brain scans, but most of the time we can't observe the brain. And besides tasks where we can have um, less invasive kinds of imaging, um, we can't really know what's going on inside. However, we can do the next best thing. We could usually see what's going on when people are looking at stuff. Um, the direct connection of the brain to vision is very important in many of our behaviors and can um, help us understand our attention and decision making a little bit better. The eyes may be the window to the soul, and by looking at what we're looking at, we can gain invaluable insights about how people learn. For example, this is the healthcare.gov website, and it's very highly studied because it's very impactful to a majority of our country, where people have to access specific governmental information. And eye tracking can help us redesign these pages so that we can make it so people can find things that they're looking for a little bit better, or can discover things that they might not know and might want to look into. These same technologies can help us look at the differences between people who can read well versus people who are learning or people with dyslexia who have different attention patterns. The size of the dot is correlated with how long the person looks at that particular thing. Um, and the jumpiness of the lines tells you where people's eyes are going. So if we can deploy some of these technologies, we can help improve not only for formal context, but for looking at websites and looking at information in our environments, like at the zoo or the museums, or any other informal learning environments that are designed. We know that collaborative work and working solo have their time and place. How we interact with people and how we interact with each other online is changing, and it's a very big springboard to jump off of to explore how our actual lives can inform or direct how neuroscience can be conducted. So something in the learning sciences that is catching on is this idea of universal design for learning, which is basically how we can improve engagement, expression, and accessibility for learners of all types across all age levels, in both your formal schooling and training, as well as when you are exploring on your own. So no single change to educational practice will lead to an instantly better society, but by connecting our lived experience in society to the fundamental neurosciences and an interest in how we all learn, we can make better experiences and make learning more accessible and personalized to everybody. To conclude, learning is contextual and happens all of the time. It's social, it's developmental. We learn differently when we are kids and when we are older adults. Can be emotional, where we have to make very hard decisions some of the time. And it causes changes in the brain, which cause changes in how we learn, which causes changes in the brain. So by learning about how people learn, we can definitely become a lot more productive and make more meaningful experiences for people everywhere. Thank you.
Great. Thanks so much, AJ. I wish I had done more Legos when I was growing up. It seems like a lot of smart people do Legos. All right, so just a reminder, if you have any questions for AJ, you can put in questions in the Ask a Question field at the bottom of the page. So please do that at any time. Our next speaker is Natalie Mastick. Natalie is a PhD student in aquatic sciences at UW and a graduate fellow with Oceans Initiative. She studies how parasites affect marine mammals in Puget Sound using historical ecology to figure out how parasite abundances in fish have changed over the course of the past century. Mastick also works to determine how parasitized the whales that eat those fish species are today using recently collected fecal samples. Please join me in welcoming Natalie Mastick.
In the summer of 2018, it felt like all eyes were on the southern resident killer whales. These local celebrities gained international attention as an orca known as J35 pushed her dead calf around for days on end in an act that can only be described as grieving. The world watched as the mother pushed her calf at the surface for a total of 17 days, over 2 weeks. Her pain reflecting that of the scientists that know the importance of each birth in this population. The southern residents are a population of killer whales that live in Puget Sound. They are well known in the area for their ongoing plight against extinction. Their residence in Puget Sound has made them a cultural symbol and an icon of the Pacific Northwest. The population is currently made up of 72 whales, and that is a number that has largely been declining for decades. Calves are especially important as they are a tangible increase in the population. Female calves represent new potential for population growth. Each calf represents a chance for the population to recover, and each death another opportunity to face the dread that many locals and researchers have for this population's future. Less than a month later, the population was struck another blow. A 3-year-old calf known as J50 was starving. She was much too skinny for her age. On the heels of J35's loss, researchers pulled out all the stops and tried something they hadn't done before. They launched an intervention. US government researchers followed J50 and tried to feed her. While they were following her, they collected a fecal or poop sample from the small group that she was traveling with. They analyzed the fecal sample and found that it was riddled with parasite eggs. Based on this finding, they prepared a deworming medication that they tried to treat J50 with, much like you would treat a dog. However, they didn't make it to her in time, and by mid-September, J50 was presumed dead. 2 calves lost in one summer. Now, we knew a lot about what these whales were going through. Until that summer, we knew of 3 major threats to this population. First was a lack of fish. Southern residents only eat fish, and they prefer Chinook salmon, yet Chinook runs have largely been declining throughout the Pacific Northwest. So there's less fish to feed these hungry whales. Second is noise. Killer whales use sound to communicate and to find their food through high-frequency sound, or echolocation. They also happen to feed in Puget Sound, which is home to a major shipping lane and a lot of commercial and recreational boats, which makes their feeding grounds loud. That makes it more difficult for killer whales to communicate and to find fish. Third is pollutants. Killer whales are apex predators. They sit at the top of the food chain, eating a lot of fish that have also eaten a lot of other things. If the fish that killer whales eat have pollutants in them, then those pollutants can get transferred over to the whales. This leaves orcas at risk of bioaccumulation, or the concentration of contaminants in a living animal over time. But we weren't looking for parasites. Parasites are generally assumed to play a minor role in whale health, so we weren't regularly monitoring this population for them. But after what happened with J50, it led me to wonder, could these little worms have done that much damage without anyone noticing? What are these worms doing that would hurt the apex predator of the ocean? And should we consider parasites to be one of the major threats to this population? To look at how parasites fit into whale health, let's first look at the world that whales live in. This is a typical marine ecosystem in the Pacific Northwest. We have a wide range of marine life, from those that live at the seafloor and in the kelp forest, to those marine mammals that live close to the surface. How does this ecosystem work? How do these different species interact? We can look at this through the food web, or the who-eats-who of the ecosystem. Now, you've probably heard of a food chain, but a food web is basically all of the food chains in an ecosystem overlapping and intertwining. We see food chains of smaller animals getting eaten by larger animals and larger animals, all the way up to those apex predators, intertwining into this broad food web. Even in this simplification, the marine food web gets complicated. There's a lot of overlap in a dynamic ecosystem. Let's look at just the path of a southern resident killer whale's diet. We see small crustaceans getting eaten by small fish that are then eaten by larger fish, and eventually they make their way up to that killer whale. But where are the parasites? Where do they fit in, and how do they end up in their hosts? Within many of these animals, there are parasites hiding. Some of these parasites have really minor health impacts, like the parasites that hang off of this dolphin's dorsal fin. Others, like the parasitic barnacle in this crab, completely take over the host reproductive system, leaving them unable to reproduce. So there's this spectrum of harm that parasites can cause, from very little to a huge burden. Some of these parasites have complex life cycles that involve multiple hosts. Let's go back to the killer whales and the parasites that were found in their poop, the Anisakid nematode. Anisakids are a type of parasitic nematode or worm that infects whales and dolphins. They are released into the ocean as eggs in a whale's poop, which kind of looks like a cloud at the ocean surface. They are then eaten by a small shrimp, in which the egg develops into a larva. That shrimp can then get eaten by a small fish, where that larva grows a little bit more. The fish then gets eaten by a bigger fish, where the larva grows into its infectious stage. As soon as that fish is eaten by a whale, the worms infect the stomach and the intestine and grow into their adult stage, which is about the length of a toothpick. They then lay their eggs, which are released back into the ocean through the whale's poop, which starts the cycle all over again. What's alarming is that there's evidence that anisakids are increasing in the world's oceans. A recent study looked at the parasites found in fish all around the world over the past several decades and found that anisakids have increased globally. This means that these worms could be infecting more marine mammals today than they have in the past. This map shows the number of records of anisakid estimates in fish around the world. But this study didn't include the fish species that southern residents eat, or any fish caught in Puget Sound. So while we see this global trend, we don't know if anisakids are increasing locally, making them a mystery in our waters. Now, you will remember that some parasites don't do much to their hosts. They're just a friendly hitchhiker. Others are more sinister. In small numbers, like anisakids are normally found in marine mammals, they appear to do little harm. They live in the stomach and may take up some of the whale's food, but not enough to cause severe problems. But when anisakid infections get more severe, they can hurt their hosts. The more worms in the stomach, the more of the killer whale's food they steal for themselves, and the more likely they are to cause major health impacts. And in an already food-deprived whale, this can be a big problem. So if these parasites are increasing in Puget Sound, they might be worse than we thought. In light of the discoveries made in J50, we can't just assume that these parasites are friendly worms anymore. So let's think about J50 again. Researchers saw things that looked like this, these tiny eggs the same width as your hair. They knew then that parasites might have been causing health impacts to J50. Since these parasites are becoming more common around the world, could they be increasing in Puget Sound? Could they be affecting other whales in the population? And could this be another stressor impacting this killer whale population's recovery? And perhaps most importantly, what will happen the next time a calf gets too skinny? How will we know what a normal, mild amount of parasites looks like compared to an extreme, bad infection? In that same summer of 2018, I was watching the whales very closely from the shores of San Juan Island. That's me looking through a theodolite. It's a piece of equipment that we use to track killer whales from land. I had spent the past several summers there researching Southern residents with Oceans Initiative. I watched that intervention play out in real time and closely followed what the researchers found. I was interested to learn more about the threat that parasites might be to Southern residents. So I went back to school. The first thing I wanted to know was how bad are these worms for the whales, both for individuals and the population as a whole. And I thought it would be pretty easy to figure this out. After all, I already knew how to detect parasites in a wild killer whale. That's how they found out J50 had parasites. You look at the poop. And actually, as hard as that sounds, researchers have been looking at whale poop for a lot of other studies. So they already have methods in place to collect fecal samples. Researchers at the University of Washington use dogs that have been specifically trained to smell killer whale poop and can locate it from great distances in the open ocean. Once they find it, researchers then scoop up the poop and use it to look at killer whale diet, hormones, and genetics as a way to monitor whale health. I've been able to take the leftovers of about a decade's worth of samples to look for parasites. So part of my research is looking at fecal samples like these at the top. We modified this a bit so that we can find super small whale parasite eggs. Once the eggs are collected from the top, I can count and identify the parasites in a sample under a microscope. Then we can figure out how many adult worms are likely to be in that whale, competing for the whale's food based on the number of eggs that I find. Another way that researchers monitor whale health is photogrammetry, or taking photos from above to see how skinny or fat a whale is and how that changes over time. Researchers at the Southwest Fisheries Science Center and SR3 have collected these photographs for a lot of the whales in the southern resident population. So I'm using these photographs to figure out if whales with more parasites appear to be more malnourished, if those severe infections might be related to poorer whale health. And by doing this, I can tell how infected a whale is at that moment and how much harm these infections might be doing to the whale, which can assist in diagnosing and monitoring the population. So that's how I'm finding out how bad these worms are for killer whales. But how do we tell if these infections are status quo or a new problem? Have these parasites been increasing in Puget Sound? When I started my PhD, I joined a parasite lab, and I learned how to detect parasites in other animals. Normally, this involves dissecting frozen, dead animals and finding all of the parasites in them. That would tell us how infected an animal was when it died. But again, I was interested in figuring out how infections have changed over time, so that we can know when it's time to raise alarm bells about a killer whale's parasite infection, or if an infection amounts to a normal, friendly hitchhiker. To look at a change in infection over time, I would need a long-term data set. And if I used those methods that I was familiar with in the lab, I would need a lot of dead, frozen whales spanning decades to see how there's been a change over time. And frankly, I don't have that kind of freezer space, even if those samples existed. So how do we time travel to look inside living, wild, endangered orcas of the past? This part of the project seemed a lot harder. But I found guidance in the Anisakid life cycle. These parasites are passed through eating. So looking at the fish that killer whales eat might be the next best thing to looking inside a killer whale itself. Okay, we can collect fish. That seems doable. But to see if there's been a change over time, we would need to look at fish collected from the past that could tell us about how these parasites have changed. But where do we go to find old fish? Well, where does anyone go to look for old things? Museums. And surprisingly enough, the Burke Museum at the University of Washington has a fish collection containing millions of fish caught in Puget Sound over the past century and beyond, all preserved in nicely labeled jars on organized shelves. If we could look inside these fish, maybe we could see what parasites were infecting them at the time of their death decades ago, and what killer whales might have been exposed to. So we tried it, and we found that these museum fish are a lot like time capsules. Think of a time capsule from the 1990s. It might have some cherished memories and some items that were trending at the time. When a fish is caught and preserved in a jar, all of the parasites that were trending in the environment at that time are preserved inside it, which meant that when we dissect a fish, we can see the parasites killer whales might have been eating decades ago. So to see what killer whales were exposed to in the past, we just need to look inside the fish that they eat that have been preserved in the fish collection over time. And thankfully, we know exactly what these killer whales eat: Chinook salmon. Awesome. Turns out, not awesome. Much like the killer whales, everyone loves Chinook salmon. So instead of getting preserved for science with the rest of the fish in the fish collection, salmon were more likely to end up on people's plates. Millions of fish in the collection, except for the one we needed to answer this question. But that's okay. We're used to being creative. That's how we got to the fish collection in the first place. So we went back to our drawing board, the Anisakid life cycle diagram. If we don't have salmon, we can look at the fish that salmon eat, like smelt, herring, and sand lance, these other small schooling fish that live in Puget Sound. It's another degree of separation away from the whales, but we can still answer the same question about how the risk to Anisakid infection has changed over time. And actually, by doing this, we can answer a lot more questions about parasites in Puget Sound, because these small fish do a lot more than just feed Chinook, which in turn feed killer whales. They really drive the entire marine ecosystem. So by looking at smaller fish like herring, hake, and sand lance, we can get a better idea of how parasite infections have changed in the species that eat those smaller fish, like humpback whales, minke whales. Dahl's porpoise, and Harbor's porpoise, the other marine mammals that live in the area. So not only are we seeing how parasite infections have changed for southern residents, we can get an idea of how they've changed for all of the whale and dolphin species in Puget Sound. So we are currently busy dissecting a century's worth of fish and a decade of poop samples, two tasks that are largely on hold right now in light of the present circumstances. So I'm not quite sure what the answers to these questions are yet. But regardless, we found a way to look inside living wild orcas to find parasites. And we found that this super unique and novel method of looking to the past works. And we're using it to recreate ecosystems of the past in order to figure out if killer whales today are more at risk to bad parasite infections than the generations before them. My work is helping figure out how parasite infections are impacting southern residents. Once I've completed these analyses, I will know how infected killer whales are today with their poop and how infected they might have been in the past through these time capsule fish. Through my research, I will be able to figure out if Anisakids are a friendly hitchhiker like we thought in the past, or if they should be added to the list of major threats to the southern resident population's recovery. By knowing more about the history of killer whales with parasites and monitoring the population for parasites today, we can be better prepared to intervene when another young whale gets sick. And we can act more swiftly to help this population have a little more of a fighting chance against extinction.
Great. Thanks so much, Natalie. On to our final speaker this evening, Nick Weber. Nick Weber is a PhD candidate in the Department of Atmospheric Sciences. His research focus is long-term weather prediction and how we might be able to improve forecasts with next-generation, high-resolution global models. Please join me in welcoming Nick Weber.
All right. Thank you, Candace. So, weather forecasts are wildly important for our day-to-day lives. Even now, during this abnormally inactive period in our social and personal lives, I bet most of us are checking the weather almost daily. I know at least I like to check before I go on my daily walks, which are one of the only things keeping me sane right now. So let's go ahead and do that. Let's check the forecast. Okay, so this is a screenshot from the Apple Weather app taken just over an hour ago. As you can see, the forecast for right now is cloudy, 54. Well, if I look outside my window right now, I'd say cloudy is a pretty good forecast for right now. How about the forecast for tomorrow, for Friday? Also cloudy and about 60 degrees. All right, that sounds pretty reasonable to me. But now let's do something we perhaps don't often do, and that's scroll all the way down and check the 9-day forecast. Okay, so next Saturday, 9 days from now, it looks like it's going to be partly cloudy and 80 degrees. That sounds great. But before I start breaking out my shorts, I think I might wait for a newer forecast. And I think many of us, including me, have a distrust for these long-term forecasts. Now, before we talk about why that is, we first need to understand where these numbers come from. So where do weather forecasts come from? Do they come from a crystal ball, or perhaps from a certain future-telling groundhog, or maybe from a honed intuition of a rebellious forecaster like in the movie Twister? Unfortunately, the answer isn't nearly as whimsical as any of these, but I think it's equally amazing. In fact, weather forecasts, the ones that we see on our phones and elsewhere, come from weather models. And what is a weather model? Well, it's basically a computer program. And in this computer program, we start by taking the Earth. Now, there's also regional weather models in which they only simulate the weather within a certain region of the Earth. But today we're talking about global models. So in the models we're talking about today, we're looking at the entire Earth. So you take your Earth, and then you divide it into grid boxes. Think basically a checkerboard wrapped around a sphere. And within each of those boxes, there's a value for temperature, pressure, wind, humidity, all the variables we care about in the atmosphere. Okay? The next step is to get values for those things. We need to get values for temperature, pressure, wind, and moisture for each of those grid boxes. In this particular plot, we're looking at temperature. Now, how do we get these values? Well, we measure them. Over land, we measure them using surface-based stations, or we also use weather balloons as well to get sort of upper atmospheric measurements. But over the oceans where we don't have surface stations, we use satellite estimates. Great, so we've used observations, and now we have a full grid of temperature, wind, pressure, and moisture. Now, we just have to predict the future. And we do that basically using mathematical equations. And they're quite complex, so I won't go into them here, but they relate these values to one another in order to predict the weather at a future time. So that's basically what a weather model is. And as it turns out, our trust in the Apple Weather app is reflective of how these models perform, which is to say, they're quite good in the short term, but a little less trustworthy once you get further out, like 1 to 2 weeks into the future. Now, why is this? Why do models lose skill over time? Well, the answer lies in butterflies, or more specifically, the butterfly effect. So in order to better understand the butterfly effect, let's add a y-axis to our graph here. And this is going to represent temperature. So the higher up you are, the warmer the temperatures, the lower you are, the colder. Okay? And we're going to start with a point representing the temperature now. Let's say it's 71 degrees Fahrenheit. And let's say that value is coming from here in Seattle in our weather model. Now, this is the value for now. And so this represents the temperature we've measured with a thermometer. This is our observation. Now, if we run our model forward in time, we might get a Seattle forecast that looks something like this. Okay? So I'm going to go ahead and get rid of all that noise. You can see in this particular forecast, we start out 71 degrees, it gets a little warmer, then it starts to cool down, then it gets a lot warmer, so maybe mid 70s up here, and we have this nice cold period after that, and the forecast ends 1 to 2 weeks later, maybe we're in like the 80s or 90s. So this is a typical temperature forecast if we were starting with 71 degrees Fahrenheit. But what if our temperature measurement wasn't perfect? In fact, it probably wasn't. There's a certain amount of uncertainty in these instruments. So maybe the actual temperature was a bit warmer. Maybe it was 72 degrees Fahrenheit. Now, what if we ran the exact same model with this value instead? Well, we might get a forecast that looks something like this. As you can see, it starts out pretty similar, but believe it or not, by the end of the forecast, we actually have, let me get out my laser here, a colder value than what we started with. What's interesting is that even though we started off warmer than the last forecast, 1 to 2 weeks later, we have a colder forecast. And that's how chaos in the atmosphere works. That's how the butterfly effect works. Now you could also imagine a situation where maybe it was actually colder than what we measured. So if we ran the same model with that slightly colder temperature, maybe 70 degrees, maybe we have a forecast that looks like this. Okay, now let's put all three forecasts together, and this is the butterfly effect. You see how at the beginning of the forecast, all three of these lines, even though they started out with different temperature values, they remain pretty close together. We're pretty confident that it's going to get warm and then it's going to cool down. But later on in the forecast, all three forecasts are wildly different. So the butterfly effect is when small uncertainties grow larger and larger and larger as the forecast goes on because of the chaotic motions of the atmosphere, leading to large uncertainty at these long forecast times. And that is why we trust short-term forecasts and tend not to trust long-term forecasts. And because of this, there are some types of weather we will never be able to predict. I will never be able to tell you with certainty whether or not it's going to rain 30 days from now. But there are some types of weather features that can help us forecast the distant future. Specifically, what I'm going to be talking about is thunderstorms, and specifically storms in the tropics, so close to the equator. Now, I know what you're thinking. How on earth could a big thunderstorm in the Indian Ocean influence whether or not it's raining here in Seattle? Well, to answer that, think about what happens when you throw a rock into a pond. Where that rock lands, there's a lot of action, right? There's a big splash. But that's not the only thing that happens in the water. The flow of the water is affected much further away from where the rock landed in the form of ripples. Well, the same thing happens with these storms in the tropics. There's a lot of action where they occur. There's a lot of rain and thunder and wind. But there's also a ripple effect that affects the flow of the atmosphere quite far away. So in short, these storms in the tropics make waves. And believe it or not, these waves affect our weather here. So just like when you're throwing a rock into a pond, the size and the shape of that rock and where the rock lands all affect what the ripples are going to look like. Well, it's similar in the atmosphere. Depending on the size, shape, or location of these storms, you could end up with wildly different ripples. You could end up, depending on what the storm looks like, with the ripple that looks like this, which would lead to cold weather here in Seattle, or conversely, a ripple that looks like this, which would lead to warm weather here in Seattle, right? So these impacts are huge, which means these storms are really important. And it links back to what we were talking about with the butterfly effect, like where very small uncertainties in temperature make big differences further into the future. It's the same thing here with these thunderstorms. So they can have major impacts on our weather. And that's great, right? Tropical storms can help us predict global weather. But of course, there's a problem because I'm only 5 minutes into this talk and I can't end here. So what is the problem? All right, let's go back to our picture of what a weather model is. So this here represents basically a modern weather model, and the boxes are the grid boxes within this model. So let's zoom in on the tropics here. Okay, and now you can imagine maybe off the coast of South America, there's this big organized thunderstorm here. Well, in our model, that thunderstorm only takes up 4 grid boxes. This is a huge, complex atmospheric phenomenon, and we only have 4 data points to represent what it looks like. To continue AJ's Lego theme from earlier, that's like me asking you to build an Eiffel Tower with only 4 Lego blocks. Well, the Eiffel Tower is quite complicated, but if you only have 4 Lego blocks, you're probably going to give me something that looks like this, because that's the best you can do. Conversely, you could also imagine there's some smaller storms off the coast of South America. Well, gosh, those are smaller than 1 grid box in our model. So for the model to represent these is basically impossible because it can't see them. They're too small. It's like me asking you to build a life-sized ant with Lego blocks. Well, an ant is smaller than Lego blocks, so this is probably what you would give me. So it looks like our models could be doing a lot better. In short, our modern weather models can't simulate these tropical storms. And importantly, they're ripples that affect our weather here. To give sort of a practical example, rather than using cartoons of storms, let's go ahead and look at this satellite image over the Western Pacific Ocean. Okay, and we're going to zoom in on this giant tropical cloud feature just off the coast of Indonesia. All right, now you can see, there we go, there's a laser. You can see there's quite a detailed structure of this storm. It's got this big sort of comma shape. It looks quite a lot like a hurricane, and I think this does in fact develop into a tropical cyclone. But aside from this big center of bright clouds and this nice tail of clouds coming off of it, you can see there's a lot of intricate details in the storms that make up this complex. This complex is over 1,000 miles wide, but there's a lot of storms within it that are only, a few miles wide. So let's go ahead and trim off these red lines representing land, and let's look at how a weather model might represent this storm. Okay, so in a weather model with maybe 60-mile wide grid boxes, that storm would look something like this. Not very impressive. You get the general gist of what this storm might look like, but you lose all the details, which are really important for how the storm operates. I mean, this looks like a low-resolution video game from the 1980s. So this is basically like pixelated Super Mario here. So how can we fix this situation? Well, I bet some of you are already thinking of the solution to this problem. Why not just make the grid boxes in our models smaller? Okay, well, that's not a bad idea. Let's see what happens when we do that. How about instead of 60-mile wide grid boxes, we make them 4 miles wide? There we go. Now we're talking. This high resolution image captures all the intricate details that we observed before in this storm. And it looks much, much more realistic, right? This looks like 2020 Super Mario. This is what we want. Great, so we have basically 2 different models. We have a low resolution model and a high resolution model. And the high resolution model does a great job at simulating these tropical storms. End of the story, right? As in these coarse models, they don't have enough detail to accurately simulate these storms. But there's a problem with the higher resolution models as well. If you make the grid boxes smaller, that means you need more of them to cover the Earth. And more grid boxes means you need more computer power to run that model. And this is the reason why we don't see the National Weather Service today using high resolution global models for forecasts. But we do have the power. It's 2020, and we are seeing more powerful computers coming out every day. This beast that we are looking at right here is the Cheyenne supercomputer. And it basically has the power of over 50,000 MacBook Pros put together. Now, we don't have the power, even in a supercomputer like this, to run high resolution forecasts every day, but we do have enough power to at least test these global high resolution models and see how we can put them into operations in the future. And I was fortunate enough to get to use this computer for my research. So what is my research? Well, in order to get there, let's briefly step through the history of weather models. All right, we're going back to sort of our grid box look at the globe. This grid box here represents what a 1980s weather model might look like. Each of those grid boxes is hundreds of miles wide. In order to get sort of a taste of what that actually looks like, let's zoom in on Washington. And you can see that Seattle, Olympia, Yakima, Vancouver, Bellingham, Portland, those are all in one grid box. Those are all represented by one value. This is clearly not going to cut it for high resolution modeling. This grid here represents a climate model. Now, a climate model is basically just a weather model, but it's run for a longer period of time. And so the grid boxes have to be bigger in order to save on computer power. So in this model, these grid boxes are about 30 to 50 miles wide. And you can see, I mean, we're definitely doing better. Yakima is no longer the same point as Seattle, but we see that the entire Olympic Peninsula is basically one grid box, and Seattle and Olympia are indistinguishable in this model. So we can definitely do better in terms of detail. All right, now we're talking. This is a modern weather model with grid boxes maybe 8 to 25 miles wide. You can see, I mean, in the zoomed out view, it looks pretty good. Those grid boxes look very, very small. And when you zoom in over Washington, you can see that all the cities I've highlighted at least have their own grid boxes now. But this is still very coarse. 25 miles is very big, especially compared to the size of many clouds and tropical clouds. So we can still do better than this. And that's where my work comes in. This is what my model looks like. The grid boxes are so small that you basically can't see anything else here in the global view or over the zoomed in view. That's because each of those grid boxes are less than 4 miles wide. Now, I should take a step back for a second because we do currently run high resolution models like this, but they're only regional models. For example, here at the University of Washington, we run a high resolution regional model that covers basically the area of this zoomed in panel here. And it works great for weather forecasts, but using a regional model is a problem because you're too zoomed in to capture the large scale motions, those ripples that are necessary for long-term prediction. And that's why we're going through all the extra work and expense of using a global model. That's over 65 million grid boxes covering the Earth. All right, so what does a forecast from this high resolution weather model look like? Well, it looks something like this. Now, if I didn't already spoil that this was a model, you would probably guess that this is a satellite image because These clouds are extremely realistic. You see them organized into large clusters, but you also see all those tiny, very detailed cloud clusters on the periphery of these larger systems, right? You see these big clusters of clouds organizing over northern Australia. You see these smaller systems around the islands of Indonesia. And you even see a hint of those large scale waves, those ripples that are affected by these tropical storms. And those ripples are better simulated in this model. These initial results have showed that this high resolution model not only does a better job at getting the clouds in the tropics, but also produces a more skillful global forecast. All right, so what does this mean for operational forecasts in the US? Well, these very early preliminary results in my research have shown that these advanced models, although very expensive to run, can improve long-term prediction. But because they require so much computer power, I've only run a few simulations, 4, right? So we need many more cases to verify whether these models are better than current operational models, to the point where we're willing to sort of pay the extra money for computers that can run them operationally. But the early results are very, very promising. And honestly, whether it's 5, 10, 15 years from now, when we have enough computer power, you can bet that high resolution global models like this will indeed be the future of global weather prediction. Thank you.
Great. Thanks so much, Nick. So we're going to move into questions. If you have a question, just a reminder, you can put it in the Ask a Question field at the bottom of the page. We're going to go in order of presenters. So I'm going to start with AJ first.
Great.
Yeah, welcome back. So AJ, you at the top of your presentation, we're talking about some students, and I was just curious how those students get into some of the programs that you work with.
Right. So I used to be a high school robotics mentor, which is very cost prohibitive for a lot of schools. But the Lego League and Lego League Junior are very accessible with kits that are in the low hundreds. Basically, students can use the Legos that they have, or if they need to, basically the most important resource that they would need to start a team is getting a very interested adult. Doesn't have to be a teacher, just has to be somebody willing to spend time with the students.
Okay.
Yeah.
And I was also wondering, you know, just thinking about this time when a lot of students are not in classrooms. I don't know if this is beyond your scope, but can you talk a little bit about some of the pros and cons of students being outside of the classroom setting and what it might mean for their learning abilities in the future?
Right. So it's a lot of speculation right now because, quite frankly, we haven't looked into online learning environments as much as we should have before this pandemic. But regarding like the directed interest of certain students, there are plenty of resources available that will help them learn a topic. Khan Academy and all of the heavy-hitting online courses, they're all highly recommended with some research backing, but that we know that massively online classrooms, they do require a lot of self-motivation. So for students, especially K-12 kids, to have that kind of motivation, they kind of have to be directed by a teacher. And unfortunately, it's very scattered on how professional teachers are interacting with students in this time.
Yeah, and it seems like a lot of the, you know, projects that students would have been working on in these classrooms need a lot of materials that students would not necessarily have at home to build a robot.
Right.
Moving on a little bit further in your presentation, you were talking about sort of 3 phases that the brain is in at any given time. And it was interesting to see the different levels of the brain. Can those phases be happening simultaneously, even though they're in 3 different sort of subsections of the brain?
Right.
They can take place at the same time, or are they happening completely separately?
They're happening concurrently. Like they are almost always on. They don't really shut each other off, but in comparison to each other and other surrounding brain regions, they might have lower or higher activity depending on what's happening. But we do know that the executive control network and the default mode network are mutually exclusive, and we do know that the salience network does help act as a switch between the two.
Okay, interesting. And then the little bit I know about the brain, it's kind of good for me to ask questions because I consider myself a very lay person when it comes to science. But I think of like when people say you learn more things, it's often described as like a wrinkle or a crease being created in the brain. I don't even know if that is a true thing, but it was making me think about how when you were showing the models of adult brains versus child brains and how networks are closer together in adult brains, meaning that they are maybe a little more efficient. Is there any correlation between what I understand to be when someone learns and is like creating a crease and the close connectivity that you were talking about?
Right. When we refer to a lot of connections, we're usually referring to really microscopic synapses, the connections between neurons in different areas of the or different structures in the brain. As far as creases, those are anatomical features that are kind of more related to, I guess, you would see more differences as people age. Brains actually do shrink a little bit, and kids actually have a lot more synapses than adults. They go through a type of pruning phase throughout all of their development as kids.
Okay.
So, yeah.
Interesting. And then I've got a couple here in the question field. So this one's from Paul. He's asking, is there a difference in quote unquote experience if it's real versus created, like online classrooms versus an in-person one, or like New York City buildings built in Las Vegas, like the recreations? How authentic do experiences need to be to really learn?
There's a lot of, like, in fact, all of the studies that I've shown, most of the time they did some version of virtual reality or a video game. So like, obviously you can't be in a brain scanner and drive a taxi. Those taxi drivers were playing a video game, and the experience was just as real to them, apparently, that they used the same types of brain regions, and we kind of back that up by looking at how their brains respond compared to more novice drivers or more amateur drivers. As far as creating authentic learning experiences, a conversation on Reddit is almost just as real as having a conversation with a person. Like, there's a different mechanism moderating that, but those interactions that you have online can be just as real and just as impactful throughout your day. If somebody downvotes your comments or somebody upvotes your comments on the other side, they can be just as impactful to the person. They could get people to think about different things when they're linked to new bits of information. And as far as building buildings in a different location and making a new compilation of structures, I guess, we do know that your brain is triggered in terms of like mapping and placement. Like, people can play video games, or people can explore different environments, and they make a mental map that is pretty stable. So people who play Minecraft might have a mental map of some of the locations that they've built. So yeah, those experiences can be just as real as physically going to places and going around.
Interesting. And then this last one is from Taryn. With the different brain phases related to learning, how are those affected by other bodily experiences like illness, interpersonal relationships, activity, etc.?
Right. We know that stress and lack of sleep and a lot of environmental insults or traumas can obviously negatively impact how people learn. If you're hungry, like the classic example is students who are unfortunately hungry during classrooms, they're not going to learn how to read or do math if they're sitting in the classrooms hungry. There are biological needs that have to be attended to, and that does kind of eat away at willpower and the your capacity to pay attention. And we do know that other things can be helpful. So not all bottom things are bad. We do know that exercise is very protective or very neuroprotective, as in it can help stave off lots of diseases as people get older. We do know that cardiovascular health and general fitness can help people, like in terms of their social engagements, obviously, how they interact with different people, and how they might go about their day. We do have schedules, and there are like early birds and night owls and stuff like that. So there are plenty of variables that are at play related to how people learn.
Great. Thanks so much, AJ. Nice job.
Yeah. Thanks.
All right. So we're going to move on to Natalie now. So I've got a couple of questions here. Can you talk about what we stand to lose with the ever declining numbers, it seems, of apex predators in the ocean?
Well, that's an interesting question, because while some apex predators we are losing, we're losing a lot of sharks, we're losing killer whales here, like I talked about, and throughout the world, there do seem to be these declines that are largely based on anthropogenic impacts. Or we're also seeing increases other places. So I think while we focus on the ones that are declining, we're not really looking at the species that are filling those places. And so an example would be in Puget Sound here. While the southern residents are declining, there are two other populations of resident killer whales in British Columbia and one higher up in Alaska that are increasing. And we're also seeing other species of marine mammals that one would consider an apex predator, like transient killer whales, increasing in the area as well. And so I think it just depends on how you look. But as we see declines, I think that's just showing a larger picture of how ecosystems are changing as a result of human impacts.
As I was listening to your presentation, started to feel a little bit guilty, actually, because I'm planning on having salmon for dinner tonight. Would you recommend that we all just stop eating salmon?
I would definitely recommend to stop eating Chinook, because we are not as picky as these southern resident killer whales, and that is their species of choice. So if we could just put that aside and leave those for the killer whales, that would be great. But another thing to consider is that we eat a lot of the same fish that killer whales eat. So a lot of those parasites that are in the fish that killer whales eat are also in the fish we eat. So another thing to consider is to make sure that your fish are flash frozen before you eat them to kill off any parasites, or cook them thoroughly.
Yes, I thought of that as you were speaking as well. Can you talk about what's the cause of more anisakids in our oceans? Why does it seem like they are growing in number?
Well, we're not quite sure. There's a theory that it could have to do with an increasing number of marine mammals. So in the 70s, a couple of protections were put in place to protect marine mammals. One was in the US, the Marine Mammal Protection Act, and then globally, the International Whaling Commission put a moratorium, so they completely ceased commercial whaling. So since that point, we've seen a really slow increase in marine mammals around the world. Some are not doing so well, as we saw with the killer whales here, but a lot of them are increasing. And a lot of these parasites will use any marine mammal as a host. So when we see an increase in like humpback whales, those humpback whales might be harboring the same parasites that infect killer whales. And so when they poop out those eggs and those eggs get transferred back into the food web, then they can end up in killer whales. So it could be an increase in marine mammals around the world.
Interesting. And then I've got a question here from Taryn. She's asking, how much of a threat do parasites pose to the long-term survival of the southern residents? Are there serious proposals for how to reduce the impact of the parasites?
That's a really great question. We don't really know how much of a threat that parasites pose right now. That's part of my research, is figuring out how big of a problem this is, because we just haven't looked at them at all. But I mean, conceivably, like I said in the beginning of my talk, there are a lot of stresses on these whales. So, I mean, if there are fewer fish in the ocean and it's harder to find those fish, and those fish have more contaminants in them, and then on top of all of that, they have parasites in them that are going to take away energy that you're taking in as a whale, then it's just a compounding issue. So on top of all the other threats, it could be just the straw that breaks the whale's back in this case. But I think seeing the impact that parasites had on J50, that calf, it's really alarming what impact they might have on younger survival, in addition to those other stressors that are causing such big problems with this population. And I think the second part of that was, are there serious proposals? Currently not, but we did see with J50 that they did try to treat her with deworming medication. So it's not out of the question that a whale would be treated for parasites by human veterinarians going forward, if that meant one more whale can survive in this population. Because at this point, the population's in such bad shape that the survival of every individual really matters.
And then I've got a follow-up on the question about anisakids. How far back do the Burke fish records go, and would you be able to tell how many anisakids there were prior to the 1970s, and see if they went back, or if they went down and then back up, if there's any trend like that to be seen?
Yeah, the fish in the Burke go back to the early 1900s and some in the 1800s. So we're definitely going to be able to see if there's been a trend prior to the 1970s, which will be super interesting to see if those changes in regulations about marine mammals might have had an impact.
Great. Well, thank you so much, Natalie. I really enjoyed your talk.
Thank you. It was really fun.
All right. And then Nick, finally, our last presenter. I have one question here from Taryn. Let's see, high-res weather models, maybe the eventual future. What do you envision as an interim solution until that computing power is widely available?
Yeah, that's a really good question. So one thing I didn't mention in my talk is that these coarser resolution models, have ways of estimating the effects of atmospheric features that are smaller than the grid boxes. So I gave the example of making a life-sized ant with a Lego block. Well, in reality, models have what's called parameterizations. So like a weather model today would parameterize the effects of clouds that are smaller than the model's grid box. So based on sort of the large scale, temperature, pressure, humidity, all those things, it can take an educated guess. And the guesses are quite good at what the clouds look like within that grid box. So in the interim, and what we've been doing for the past 20, 30 years now, is trying to make those parameterizations more realistic. We still have a really long ways to go. And that's probably what the bulk of the research out there is doing right now, trying to improve those estimations of small scale processes. But also the other thing we can do in the interim is keep doing those regional models at high resolution, like we're doing here at UW, and make those domains bigger, like run that resolution over the US and then maybe over larger and larger domains. Just sort of keep inching our way to the point where, you know, we have the infrastructure to run models like that. But it will at least be 5 or 10 years before we see models like the ones I'm running anywhere near operations, probably.
And just sort of a follow-up to that, what exactly will it take? I imagine those are more expensive, take up more space, or like what will it take for us to get those bigger computer systems?
So they don't need to be that big. NOAA does not have the most powerful supercomputers in the country. It doesn't need to be that crazy. Like after Hurricane Sandy, for example, we got a bunch of funding. NOAA got a lot of funding, and that's how we were able to upgrade our current models. So if I'm being realistic, what will it take will be some other phenomenon like Hurricane Sandy that convinces people that we still need to improve our models here in the US, and there's still benefit that we can get out of that. Because what Hurricane Sandy did was it proved that the European centers model was better than ours. And so that's how we got funding, so we can improve our model to be as good as theirs. Also, we're not as good as theirs yet. We're like 3rd or 4th place in the world right now. So we still have a long way to go. But yeah, unfortunately, I think the answer to your question is somewhat political, I guess, because the resources exist.
So we need sort of an arms race.
Yeah, I guess.
For weathermen. I was wondering, as you were talking about storms, you mentioned that this is just a very basic question, probably. You mentioned that a big tropical storm is just a bunch of small storms. Is that true? Is that true for any big storm that we see?
I mean, that's fairly reductive. I guess, like, if you were to look at a hurricane, you could make the argument that it's a bunch of smaller storms that have organized into this larger feature. They certainly start as smaller storms, but I probably would not call like a hurricane just a group of storms. I would call it its own phenomenon, but you need to be able to simulate the storms that get organized into that huge circulation. So
okay.
I guess, yeah, I never thought about that before.
They call it a system, I guess, a weather system or something.
Right.
I wonder if you were tracking or just following at all the major, they were calling it a cyclone, I guess, that just hit India. And given that storms like that, it seems, can affect us, can you kind of talk through like how that particular one would? Did you follow that one at all?
I actually didn't follow that one at all. I have a dissertation due at the end of next week, so been pretty busy. But I can say, and so rotating storms like that, like typhoons and hurricanes, they have an especially large impact on weather in the mid-latitudes where we live when they transition from being a tropical storm to an extra tropical storm. Basically, when they leave the tropics, they transition into a completely different type of storm entirely. And that has huge impacts on global circulation. So in predicting storms like that, it's important to know exactly where it's going to be and of what intensity. And our hurricane and typhoon and tropical cyclone, those are all basically the same thing. Our track forecasts for those are currently not very adequate, I would say, with current global models related to the problems that I was bringing up in my talk.
It's interesting. It strikes me that as I was growing up and watching cable news with my parents, I would see the weatherman all the time and see these like, visuals that they would give. And now that a lot of us get our news in other ways and have to specifically look for the weather and specifically look for those maps, I'm far less exposed to seeing weather patterns just in the predictions that I look at these days.
Yeah, that's a good point. Most of people's weather exposure now is what I showed at the beginning of the PowerPoint. Like, it's just a list of numbers wherever you are. So I think because of that, people sort of forget that there's sort of large scale phenomena associated with those numbers. And I think that's a really cool point, that it might disconnect them with sort of the geography, the sort of spatial aspect of weather that you would get forced to watch when that's what was on the news.
Right. Yeah. In the green room, you were mentioning that you're moving to the East Coast. Are you comfortable talking about what you're going to the East Coast to do?
Sure. Yeah. So I'm defending my PhD at the end of next month over Zoom, unfortunately, but that's the way it goes. I've actually got a position as a weather researcher for an investment company in Connecticut. So I'll be doing a lot of what I'm doing now, trying to find out ways that we can basically improve our long-term weather prediction here in the US. And from current forecasts, though, rather than from inventing a new model. I didn't invent this model. Using a new model to get better forecasts, I'm going to be trying to see how we can squeeze out more predictive skill from what we currently have.
Interesting. All right. Well, great. Thank you so much, Nick. And thank you to all of our presenters. This has been a really informative evening. And thank you to everyone watching. If you are interested, we are having our final program in this series, UW Engage Science. The final one is on Monday, June 1st at 6 p.m. If you're interested in more town hall content, you can follow this Crowdcast page by clicking the follow button at the top right of your screen. And again, AJ, Natalie, Nick, thank you so much for your presentations tonight, and I hope everyone has a great evening.